Okay, good afternoon. Today is faculty notes day, so we will have two talks given by professors. The first speaker is Davide Ancona. He's a professor here working on programming languages and software verification, and today he will talk about a verification technique called runtime verification and how to apply it in the context of distributed systems.
Okay, so thank you, Luca, for your presentation. For people attending this seminar. So today I will talk about a research topic I've started working on some years ago. First year should be 2012. And together with several people here in the department, I will mention some of this work. On runtime verification and especially in the context of distributed systems. So here is the outline of the talk. So I will give a brief introduction to runtime verification and applications. Then I will give some more details regarding runtime verification for distributed systems and give you just a very simple example to show that we also work on a real tool from some concrete stuff. Okay. We show you some few implementation details of the tool we're developing together with Luca and other people. And then I want to point out interesting collaboration opportunities to try to involve some other more people, more colleagues in the department, if possible. And then just a selection of the references. Okay, so let's start. So what is runtime verification in a nutshell? Well, runtime verification is a method, so collection of different techniques based on dynamic analysis to ensure correctness of a system. That is to ensure that some properties, some good properties of the system are verified. And so this research topic is relatively young, even though the idea of applying dynamic analysis is quite old. Systematic study and use of this approach has started rather recently. Just to have an idea, the main conference on runtime verification, which is called Runtime Verification Conference, started in 2001. So it's a recent event. Okay, so with this picture, I will try to introduce the main concepts and how roughly works runtime verification system. Okay, and a tool that supports runtime verification. So here with this gray color, you have the only two inputs of the system, which are, of course, the system you want to monitor and verify, okay, and the properties you want to verify, and these properties are formalized by some specification. Okay, so these two are the inputs. Then we have so what have to be produced in order to have a tool supporting runtime verification. So we have to work on instrumentation of the system, and we have to synthesize from the specification what is usually called a monitor. Okay. So what happens at run? So when we want to verify the properties specified by this specification, so
Can I ask a question? Here you have this feedback, which I find a bit strange. Is it directed to the instrumentation?
No. Let me explain how it works. Okay. So you provide specification a system, then you have to implement an instrumentation of the system, and we will see what is the purposes of this instrumentation. and you must be able to synthesize from the specification a monitor. Okay. Then when you run your system, your tool, then what happens is that the purpose of instrumentation is to generate the observable relevant events that have to be monitored by the monitor. Okay. And the specification represents what? Represents the semantics of the specification is a set of event traces. Okay? So traces of events that are produced during the execution of the system, and these are the good traces. Okay, the traces that satisfy your properties. So the instrumentation sends the relevant events, observed events, to the monitor, and the monitor checks these events. And the output of the monitor, there are two different kinds of outputs. What is usually called a verdict and a feedback. So feedback is an optional output, we will see later on. and feedbacks are sent back to the system if we want to use runtime verification also for handle errors, explicitly. Okay. Otherwise, if you use runtime verification just for verifying your system, testing your system, then you just need the verdict. Okay, so the verdict is some value in some logic. So it's not necessary to be the classical Boolean logic. Most of the time, it's a many-valued logic. Okay, and so what else? Okay, so instrumentation. So the instrumentation, there are two kinds of instrumentation. There is a static instrumentation. This means that the system is, the instrumentation is at the source level, so you have to generate through the instrumentation a new system and then execute this new system. Otherwise, the instrumentation can be dynamic. This means that events are generated thanks to the use of the runtime system supporting your language, programming language. Okay, and then the monitor can be and the whole process can be either online or offline. So runtime verification is online when actually we are checking the behavior of the system at runtime, really at runtime. But sometimes the monitor can works offline. So what we do usually, we run the system, we collect in a log file, for instance, all relevant events, and then afterwards, after the execution has terminated, the monitor checks the trace. Okay. Okay. So I think so. Here are main concepts. Okay, so okay, another thing that I would like to say about the instrumentation and the specification. So here from the picture, it seems that the specification and the instrumentation are strictly separate, but it depends. So there are approaches where the specification and the instrumentation are mixed together, while there are other approaches where they are kept strictly separate. Okay. So motivations for runtime verification. So the motivation starts from the fact that there is no silver bullet for solving the problem of software verification. So we all know that there are several approaches, and with pros and cons for physical form of static verification. Of course, you have strong correctness guarantees. Okay, your check is in a sense exhaustive, but you have scalability issues, especially when your system or the properties you want to prove are very complex. While software testing, of course, scales very well, but it's not exhaustive. So you don't have guarantees as strong as for formal static verification. So how about runtime verification? So runtime verification is very similar to testing in a sense, because of course your verification is at runtime, so it's not exhaustive, okay, as testing, but scales rather well, okay. So you are able to prove quite complex properties. And with respect to testing, there are also some differences. So let's see what. We will see in our example, for instance, that with runtime verification, you have lower chance to have false negatives in case of non-deterministic behavior. So you can capture problem with non-deterministic behavior that cannot be captured with testing. In general, there is no strong dependence between the specification language and the underlying language used for implementing your system. Okay, so they can be separate, and this is good for interoperability and the use of your properties. So you can just express your properties once for all, and then use your specification for checking similar properties of different systems. And, as I told you, if you want to use runtime verification not only for testing, but also for trying to handle errors during the execution, so at deployment time, so during deployment, not just for testing, then you have opportunities for runtime enforcement, for protection, and so forth. Okay, so why are interested in runtime verification for distributed systems? Well, for several reasons, also for historical reasons, because we started these research topics in the in the area of multi-agent systems, which are by definition distributed systems. But also because debugging and testing distributed systems is it's hard and time-consuming. Okay, and here I'm not talking about unit testing, but I'm talking about acceptance testing. So trying to prove global properties of the system. Okay, not local properties. As I told you, runtime verification works well with non-determinism, and of course with distributed systems, non-determinism can occur very frequently. Okay, and another interesting thing is that your properties, the properties you want to ensure, may involve different components, more components, which are heterogeneous. Means that they are implemented with different languages. Okay, so in this case, you want to keep well separate the specification language from the simulation. Okay, and necessarily, your monitors must be distributed, okay, to be able to interact with different components of your system. Monitor the global behavior of your system. And you want to have this separation between, the specification of your properties and the way your components are implemented. So to have just a specification language which is system agnostic. Okay, so one specification language for different systems. Indeed, what we have done in these years, we have been used the same specification language to prove verification through runtime verification for different kinds of systems. So we started with Viviana and Angelo, as I told you, by using runtime verification for proving the correctness of interaction protocols between agents in multiple systems. We've tested this approach with several platforms, at least two, they are based on Java and Prolog, so different languages. And then with Luca, Giorgio, Maurizio, Marina, Filippo, we also use runtime verification for verifying properties of Node.js applications. So Node.js is a JavaScript framework which is used for developing distributed components. And as you can see, we are using the same language, but of course the relevant events for runtime verification can be different. For instance, the focus in a multi-agent system is on message exchange between agents, while in Node.js, the relevant events, as we will see, are function and method calls and the execution of the callbacks associated with this function and method call, because Node.js is based on asynchronous programming and this event-based, event-driven model. And then we have used again the same language for runtime verification of Internet of Things IoT systems by using Node-RED. Okay, so Node-RED is a tool that allows you to define Internet of Things systems based on flow programming. It's a very interesting tool that is heavily used in the fields of IoT systems. Okay, so let's have a look at a very simple example based on runtime verification for Node.js. And we will show how runtime verification can be used to deal with non-determinism. So here we have a very simple code fragment that just implements a very simple HTTP client, okay, sending some request, some post request to a server in a loop, okay? And so what is sending is just a sequence of integers, nothing very interesting. But here there is a bug, because so what we are doing here is we create a new object request, and then we can send a request to the server by using this method end. Okay? So the problem is this method end has a second optional parameter, which is a callback. And the callback is the code that will be eventually executed after we are sure that the request has been sent to the server. Okay? So here we are not using the callback. So since handler is in a synchronous function, this means that we are scheduling all the requests issued in this for loop in non-deterministic way. Okay? So, so it may happen that the server will receive the integers not in the standard order as specified by the loop, or for large numbers, for max, for this constant, you might also have some error because we are trying to allocate too many sockets for the communication. But we are scheduling all these requests just in parallel. Okay. Oh, the problem is that it's very difficult to catch this this bug, at least if the number of loops is a few hundreds. So you want to send a few hundred requests, then you can really observe any problem, because if you test the server, you just see that the server receives the integers in the expected order. Okay? So it's very difficult to catch this problem by using testing. Here is the correct code. So the correct behavior is using a callback. Say, okay, you can send the next request only when you are sure that the first request has been sent. And how can we detect the problem with the runtime verification? So we have to formalize the property. So here we have elements. We have here we have first we have to know which are the relevant events for our verification. In this case, there are these three kinds of events. So we have to know when HTTP.request has been called and return the corresponding value, which is the request object. When we call the method end on this request object, and when the corresponding callback is A, is executed. Okay? So here is an example of the expected correct event trace. Okay, so first I want to call the request method that will return a new object. Then I want to call on this new object method end. Then the callback associated with this method end must be executed. And in order to do that, the instrumentation has to associate with this call a unique identifier. Okay, so that we are sure that this callback was the callback that we have passed to this invocation. And after we have executed the callback, we can continue by calling again the request and so forth. And at each loop, of course, we have different request objects that are created, and of course, different identifiers. And you know the value of this variable only at runtime. So it's actually a parametric specification. So here is how can this can be formalized in our language. So of course the length of this trace is arbitrary. Okay. And here is the formalization. So the formalization is, okay, you have to introduce these two variables, okay, that are bound when the relevant events are detected, and this accounts for the fact that our specification is parametric. Okay? So when you detect the HTTP request as being called and as return a value, this value will be associated with this variable rec, and then will be used later on where you expect this to match with the call of end method on rec. Okay, and this will produce an identifier, a unique identifier for that call, and this value will be used here when you want to be sure that the callback associated with the invocation of your method end will be executed. Okay, and then here the specification, of course, is recursive because this can be repeated an arbitrary number of times. Okay, so if you try to if you verify this cloud version with this against this specification, what you get is this behavior for what concerns the generated monitor. So the generated monitor receives this first event that is generated by the instrumentation, and the verdict in this case is so far so good. Okay, just you just have a request, then you send the request by calling the AND method, and again, this is data, so monitor says, okay, so far so good, and running the file. But then, here, you don't have any callback, because there is no callback here. Okay? So no callback will be executed, and in the loop, the next event that will be registered is the call to the request again, and then you have an error. Okay. Some implementation details. So this works, really works. We have been working on the tools, and we're still working on that. So in this case, instrumentation is based on this tool, Jalan 2, which performs static instrumentation. So actually, what happens, you transform the original Node.js code in an instrumental Node.js code. Then the specification you have seen produce automatically through Antler the monitor, which is written in product. So it generates code automatically from your high level of specification. And then the system is executed, and this is a really distributed system, and the two components interact each other with a WebSocket protocol, which is quite efficient protocol for handling real-time data exchange. And events are encoded with JSON as a JSON object. Okay. Interesting research direction. So there are ongoing collaboration. There is a seed project with Nicoletta, Locetti, and Maurizio and Luca, how to see how testing and runtime verification can be used for verifying machine learning algorithms, and still ongoing work on how it's possible to verify IoT systems by using runtime verification. But then there are other interesting directions on different topics. For instance, theoretical computer science, programming languages, software engineering. In general, we are interested in studying the expressive power of our specification language, either on the theoretical point of view, but also on the software engineering point of view. Whether it's possible to use this language for expressing timed properties, and it's possible also to support the tool with some graphical applications. Security, so there are several works. The idea is not new to use runtime verification for security, because with runtime verification you can monitor malicious behavior, and then you can use runtime enforcement to avoid that some malicious behavior can really damage your system. Natural language processing, also this can be very interesting, because what we are doing at the moment is mining of the properties from the documentation. Okay? And it would be nice if there would be some semi-automatic way for deriving the specification used by runtime verification in a semi-automatic way. And then, of course, for people more interested in system implementation, there are issues concerning software performance evaluation, because, of course, all these have an overhead, and we want to measure this overhead concerning the fact that the code is instrumented and the monitor may have some efficiency problems, and how it's possible to reduce this overhead. Okay. So if you want, here there are some selected references concerning runtime verification in general and the main papers on the collaboration mentioned. Thank you.
Are there any questions?
So for you, a specification would be just a set of infinite traces. What is a specification in this context?
Okay, so the semantics of this specification is an infinite set of traces. And the traces
of infinite.
Okay, and the traces, yeah, and the traces here the traces are infinite. Okay. Then of course you can also specify finite traces. So if you know that at a certain point your system is allowed to terminate. So here for simplicity I've only given a specification where these loops go forever, but of course you may also take into account the fact that sooner or later you want to execute it.
And from the point of the formal language, could you use something like linear time temporal logic to specify properties, or you?
Okay, so as I told you, no, so our approach is based on the semantic of the language is expressed with a level prediction system. So, usually there are two different approaches for specifying properties in runtime verification. Either by using formalities like regular expressions or context-free grammars, or using some temporal logic. Okay. And so our approach is more similar to formalities like context-free grammars, but it's more expressive. So, for instance, it's possible to specify languages which are non-context-free languages. And there is some work where we compare the expressive power of our formalities with linear temporal logic.
So what's the result of this comparison?
Yeah, so the problem with linear temporal logic is that if you use linear temporal logic for runtime verification, then you lose some expressivity, because of course with runtime verification you only verify finite prefixes of traces. So for instance, the until cannot be verified, really, because you don't have a finite verdict. If you expect for properties to be verified sooner or later, and you're doing this not with model checking but runtime, then you lose specificity. And then in fact it's called, the formal is called LTL free, because we need to introduce this free value logic, because the verdict of the monitor is not a Boolean value. And if you compare with this logic, then our formality is more expressive.
Any other questions?
Just a curiosity, you mentioned the relation with machine learning or something.
Yeah.
What are your ideas about it?
We started working on this.
Okay.
So we don't have very precise ideas on that, but what we are looking to start exploring is that, of course, I mean, machine learning is, especially in the context of IoT systems, it's based on the fact that firstly you collect a lot of data from sensors, okay, and the correctness of the output of the machine learning outputs of the algorithm, machine learning output, depends also on how the data of the sensors are trustworthy. Okay? So, for instance, what would be interesting is to use a runtime verification for verifying that dynamically data coming from a sensor network and to filter out data that are not correct according to some simple analysis. And then, of course, using machine learning for refining this. Okay, so in a sense, it's a loop where you use on one side refine verification to enhance the input to machine learning algorithms, and then runtime verification can reuse the output of machine learning algorithms for making some more precise analysis. But we really started this project, and it's still working on it, and we still have to work on this.
Okay, if there are no more questions, then let's thank Davide. Okay, second speaker of today is Barbara Catania. She's a professor here working on